Hi, today let's look into the question of deleting nodes having greater value on the right. That is, we simply need to remove all nodes that have a node with a greater value anywhere to the right, right in the linked list. So at the end, we need to return the head of the modified linked list. Let's say we have this linked list, let's say 12, 15, 10, 11, 5, 6, 2, and 3. Here, since 12, 10, 5, and 2 are elements which have greater elements on the following nodes. So after deleting them, the linked list would look like 15, 11, 6, and 3. So basically we deleted 12, we deleted 10, we deleted 5, and we deleted 2. We are left with this linked list and this will be the answer. So now let's look into the recursive approach first. We have the linked list 12, 15, 10, 11, 5, 6, 2, 3, and null. This problem depends on the right side, so the recursion method naturally fits here. So we go till the end of the list because the last node has nothing to its right. So for step 1, node is 3. So the right side max will be 3, so we keep it. And for step 2, node equals to 2. And since 2 is less than 3, we gotta delete 2. So we delete 2. Okay. Now for step 3, node is 6. Since 6 is greater than 3, we keep it, and now the right side max will be 6. Step 4, we have node equals to 5. Since 5 is less than 6, we delete 5. Next, step 5 will be node 11, and since 11 is greater than 6, we keep it, and the right side max will now become 11. Similarly, we have the next steps as 10 is less than 11, we delete it. 15 is greater than 11, we keep it, and the right side max will now become 15. And finally 12 is less than 15, so we delete it. So now we are left with 15, 11, 6, and 3. So this will be the final linked list. For this entire process, the time complexity will be big O of n, and space complexity will also be big O of n. So the time complexity will be big O of n because we visited every node once, and the space complexity is big O of 1 as well because we are using a recursion stack here. So this method is pretty elegant, but it is risky for large lists. Alright, let's code this problem using a recursion approach. So this function takes the head of the linked list and returns a modified head after deletions. Let's first tackle the base case of recursion. Like if the node is the last node, then there is nothing on its right, so it can never be deleted. That is, if head dot next is none, then we simply return this node, return head. The thing that is to be emphasized here is that every recursive solution must have a clear base case. Now let's recursively process the rest of the linked list. That is, head dot next is self dot compute of head dot next. So why are we doing this? So this particular step ensures that when recursion returns, the right side is already cleaned up. So head dot next now points to the correct sublist after deletion. In simple words, we are just fixing the list from right to left. Now we gotta compare the current node with the node immediately on its right. So if the current value is smaller, it means there exists a greater value on the right. That is, if head dot data is less than head dot next dot data, then we return head dot next. That is, this node must be deleted. Returning head dot next effectively skips the current node. And one important clarification regarding the linked list is that we are not physically deleting the node, we are just changing the links. So if the current node is greater than or equal to the right side, then we keep it. So we simply return the current node as a part of the answer. So we return head. Okay. Let's say we have this test case that we already discussed. Say we have 12, 15, 10, 11, 5, 6, 2, 3. Recursion goes till 3 and then comes back comparing one node at a time. Whenever a node finds a greater value on the right, it gets removed during backtracking. Now let's go ahead and run the code. As you can see, we are able to delete all the nodes having greater value on the right. Okay. So each node is visited exactly once, so the time complexity is big O of n. However, recursion uses stack space, which in the worst case can go up to big O of n. So this solution is elegant and easy to understand, but for very large linked lists, regression may cause stack overflow. That's why an iterative reverse based solution is usually preferred in interviews. The previous approach was a brute force approach in a way. So now let's look at the optimal approach. Let's say we have the linked list 12, 15, 10, 11, 5, 6, 2, and 3. We've taken the same linked list. Now let's reverse it. So we will be having 3, 2, 6, 5, 11, 10, 15, and 12. The idea is simple. Checking the right side repeatedly is expensive, so we reverse the list. Now the right side actually becomes to the left side. Now instead of greater on the right, we now check smaller than maximum seen so far. So we have max as 3. Okay. Now at node 2, at node 2, since 2 is less than 3, we delete it. At 6, since 6 is greater than 3, we keep it and max will become 6. And similarly at 5, 5 is less than 6, so we delete it. At 11, since 11 is greater than 6, we keep it and max will become 11. At 10, 10 is less than 11, so we delete it. At 15, 15 is greater than 11, so we keep it and max will become 15. Similarly, the last one at 12, since 12 is less than 15, we delete it. So the remaining list, which is still not reversed right now, will become like 3, 6, 11, and 15. Now all we gotta do is we simply gotta reverse it. So it becomes 15, 11, 6, and 3. Therefore, we transformed a right side problem into a left side maximum problem. And here the time complexity will be big O of n and space complexity will be big O of 1. And therefore, it is the most optimal and expected solution. So let's solve it using the iterative reverse based solution. We gotta first write a helper snippet that helps us reverse a linked list iteratively. So let us define this function as reverse, which takes in both self and head as the input. Okay, now let's initialize the pointers. We have a previous pointer that is initialized to none and a current pointer that is initialized to head. So the previous pointer will track the previous node and the current starts from the head. Now we should reach the end of the list. We should iterate till we reach the end of the list. That is, while current, we got to store the next node so that we don't lose the rest of the list. So therefore, next node is current dot next. Okay. Now let's perform the actual reversal step. We flip the pointer here. That is current dot next is previous. Okay. Next, we got to move the pointers forward. That is previous is current and current is next node. Okay. And at the end, previous becomes the new head of the reverse list, ring list. So we simply return previous. Okay. Now on to our main function. Let's define it as compute, and it takes in both self and head. First, we reverse the linked list, so the right side becomes left. For that, head is self dot reverse of head. So this is the key transformation of the problem. Next, we initialize max value with first node of the reverse linked list. That is, max value is head dot data, and current is head. So basically, this tracks the maximum element seen so far. Now we traverse until second last node because we compare current dot next. So while current and current dot next, if suppose current dot next dot data is less than max value, that is, if the next node is smaller than the maximum seen so far, we delete the node just by skipping it. That is, current dot next is current dot next dot next. Notice that we do not move the current here, and if that is not the case, current is current dot next and max value will be the data of the current node. Okay, right. But if the node is greater, we keep it and we simply update the maximum. Now after deletion, the list is reversed, and so we reverse it back. Therefore, we simply do head is self dot reverse, and finally return head. Okay, so basically we return the modified list in the original order. So let's go ahead and run the code. As you can see, we have got the same output as before. So now let's look into the other approach. Let's look into a monotonic stack approach. This approach of monotonic stack is another interesting approach to tackle this problem. Let's take the same linked list 12, 15, 10, 11, 5, 6, 2, and 3. If a node finds a greater value on the right, it must be removed. So we maintain a stack where the values are always decreasing. So let's start by pushing 12. So compare it with C15. So basically we have a stack and we push 12 in it. Now compare it with the top of the stack. And since 15 is greater than 12, we basically pop 12 and then push 15. Okay, so basically the stack becomes this. Okay, now C10, the next node. Since 10 is less than 15, we basically push it. So the stack becomes 15 and 10. Similarly, see the next node 11 and compare it with the top. Since 11 is greater than 10, we pop 10. And now we compare 11 with the top of the stack. So basically the stack will become 15 after popping 10. So we basically compare 11 with the top of the stack now. So since 11 is less than 15, we stop popping and now we push 11 inside. So the stack becomes 15 and 11. 10 is deleted because 11 is a greater value on its right. So let's see 5 now. 5 is less than 11, so we basically push it. So the stack becomes 15, 11, and 5. This will be the top. C6. 6 is greater than 5, so we pop 5. And 6 is also less than 11, so we stop it here. So we push 6 after that. So the stack becomes 15, 11, and 6. Next node will be 2. So C2. 2 is less than 6, so we basically push it. So the stack becomes 15, 11, 6, and 2. Now compare step C is 3 when it is at node 3. 3 is greater than 2, so we pop 2. But 3 is less than 6, so we stop it here and then push 3. So the stack becomes 15, 11, 6, and 3. So the final stack content should be seen from bottom to top. So the content will be 15, 11, 6, and 3. Every node is pushed and popped at most once. That's why this process is linear. So the time and space complexity both will be big of n, and this can be used as an alternate approach. Alright, in this approach we use a monotonic decreasing stack. Whenever a node finds a greater value on its right, it must be removed. For this we need to create a dummy node with a very large value. Let's say the dummy is node of float of infinity. And let's also initialize the stack and append the dummy into the stack. So stack dot append of dummy. Okay, so this stack will store nodes in decreasing order. Now we start traversing the linked list from the head. Therefore current is initialized to head initially, and we gotta process each node one by one. So while current, and now we gotta pop the smaller elements. That is, if current node is greater than the stack top, it means the stack node has a greater value on the right. Therefore, while stack and stack, the top of the stack is less than current dot data, then stack dot pop. Okay, so we pop it, effectively deleting it. The point that is to be noted here is that each node is popped at most once. Now we connect the current node to the last valid node in the stack. Therefore it becomes stack of -1 dot next is current. Okay, so this builds the linked list in correct order. Now we push the current node into the stack. Therefore stack dot append of current. Now it may serve as a left neighbor for the future nodes. Now we got to move forward, move to the next node in the list, that is current is current dot next. So for the final checkup, we terminate the final node to avoid any leftover links. Therefore, stack of -1 dot next is none, and we simply return dummy dot next, that is dummy dot return dummy dot next. So dummy dot next pointer gives us the final modified list. So each node is pushed once and popped once. So the time complexity is big O of n, and stack can store up to n nodes, so the space complexity is big O of n. So let's go run this code. As you can see, we are able to get the right output here. Thanks for watching.